Hello and welcome to 6.4 Inverse Trig and Right Triangles. This should be a review lesson on inverse trig and geometry. And if you recall, inverse trigonometry is used to solve for angles in a triangle, in a right triangle. So, right triangle. So anytime we have two sides, you're given two sides. Given two sides. So if you're given two sides of a triangle, like we have in example 1, you should be able to solve for actually either one of these angles. And it's actually important to note that this should be a right triangle. So the square should be there. Now, I have three dashes marked, dashes here to signify inverse trig, and for the most part, we focus in on only sine, cosine, and tangent. Inverse trig, or inverse sine anyway, is sine to the, it looks like it's pretty much to the negative first power. That is what inverse sine looks like. Cosine is the same thing, cosine to the negative first power, and then tangent to the negative first. These all represent inverse functions. These are the inverses. Okay, and you use this to solve in your calculator for angles in a triangle. If you notice in our calculator, sine, cosine, and tangent are directly in the middle of our calculator, and in order to access the inverses, you have to use the second button, because sine, inverse cosine, and inverse tangent are all written in blue. So when we do this particular, these types of problems, you have to use second and then the trig function that you need. So let's try this first one. Solve for theta. Well, looking at this triangle, we have 10 as the opposite side of this particular angle, theta, and 50 would be the hypotenuse. The trig function that we would have to use here is sine. So we do sine of theta is equal to 10 over 50. If you want to reduce this, you absolutely could. You could write this as sine of theta is equal to 1 over 5. It doesn't make a difference either. Whichever problem you do into your calculator, you will get the correct answer. I'll show you in just a second. So, in order to actually solve for the angle, we need to get rid of the sine. And the way we do that is we multiply both sides by inverse sine. And then I'm going to put inverse sine on this far right side, and this is what I'm going to do. Anytime you use any sine or cosine function, an open parentheses starts, especially in a calculator. So what we're going to do is we're going to actually put this 1/5 into that part of the calculator, or into the parentheses. Inverse sine and sine cancel out, and we get theta by itself. So pulling out this calculator, we're going to do second and then sine. Well, first of all, let's make sure we're in degrees. We are. So second, sine, and then you can see inverse sine pops up. Open parentheses also pops up, and we do 1 divided by 5 inside the parentheses. We get 11.5. So the angle here is 11.5, and I didn't say what we should round to, so let's just round to the tenths. 11.53 just rounds down to 11.5 degrees. Now I want to show you that if you did inverse sine of 10 divided by 50, you should get the same answer. And you do, because these having those lengths is the same ratio, it's the proportional, and it just means that the angle will still be the same. Okay, so let's take a look at number 2. So that's how you use inverse trig to solve for an angle in a right triangle. Example 2, we actually have a word problem, and this is going to be pretty much a segue into our next lesson. A 40-foot ladder is leaning against the wall or a building. If the base of the ladder is 6 feet from the building, what is the angle formed by the ladder to the building? So we need to draw. So we could do one of two things. Well, we could draw the ladder first. Let's draw it from left to right. We could draw a wall or a building it's leaning up against, and then we could draw the ground that it is leaning against. So we know that this ladder is 40 feet. So we would say the ladder itself is 40 feet. The base of the ladder is 6 feet away. And this is a terribly drawn ladder in terms of scale. So 6 feet away from the wall, obviously mine is not drawn to scale. It does not look like it's 6 feet compared to the 40 feet. The question then becomes, what is the angle formed from the ladder to the building? So we would consider this part of the triangle. Hopefully you see this right triangle being formed. So that angle is formed. We're going to call that the angle, we would call that the angle of elevation. Hopefully you remember that, and then we're going to talk about that, like I said, in the next lesson. But we want to know what that angle is. So if you want to redraw this, just looking at it as if it's a right triangle, you absolutely could. And you could fill in the information. This is theta, this is 6, this is 40, and then we could actually solve. So the 6 feet is the adjacent side, 40 is the hypotenuse, and we would have to use cosine in order to solve this. So cosine theta in this particular case is equal to 6 over 40, which can be reduced, but as you saw in the last problem, you don't have to reduce it, you will still get the same answer. So we would multiply, or we would inverse cosine on both sides. Open the parentheses, close it, take this 6 over 40, throw that in there. Inverse cosine and cosine cancel out, and we should get theta is equal to, and this is where our calculator kicks in. Second, cosine 6 divided by 40, close parentheses, 81.37, which would round to 81.4. So our angle would be 81.4 degrees. All right, good. Now our last example of the day. Basic trig on an interval. Solve for all of the angles between 0 and 180 for sine of 0.4. Now this is the fun part. If you remember the unit circle, 0 starts here in this bottom right, or on the far right side. Let's do this in blue so it actually stands out. 180 degrees is over here. So we're looking for all the angles between this interval, where we would have sine of 0.4. Now, the reason why this works is because the angle is positive, so we should know that it should land on that interval. Okay, so let's take a look. Theta is by itself, or we want to get theta by itself, so that means we need to get rid of sine. So we would multiply, or we would inverse sine both sides. And even though this is a decimal, you could still technically do this. You could take this 0.4, you could throw it into your calculator, and it will still work. We would have theta is equal to, and the reason why this works is, since it's a decimal, is if you really, really think about this, 1/5 is also can be written as a decimal. 1/5 is 0.2. If you put 0.2 in here, you will see that it will actually equal here. Watch, inverse sine 0.2, close parentheses, and you get that same 11.5 that we got in our first problem. So you could see that it works. So in this particular case, we're going to be doing inverse sine of 0.4, close the parentheses, and we get 23.57. So what this means is 23.57, or we could say 23.6 since we're rounding to the nearest tenth. 23.6 degrees. What this means is on this interval, we definitely have one angle here at 23.6 degrees. But what we also want to figure out is where is the equivalent point on this interval? Well, if you remember, anytime we had, for instance, like 30 degrees, the equivalent would be directly across. Same thing with 45, it would be directly across, and 60 would be the same thing. It would be horizontal, we would draw horizontal lines. So wouldn't it make sense to do the same thing here? Absolutely, it should. So if we really consider this, if it's 23 degrees in this direction, from starting at 0, it would be 23 degrees subtracted from 180. It's kind of like your terminal points. So if you subtract, for instance, 180 degrees, and you subtract that 23.6 23.6, you should get a second value, 156.4 degrees. And that is the second value that you would get on this interval. Okay, so we have two answers here. 23.6, and let me actually extend this, and 156.4. Those are the two angles on that specific interval. All right? All right. So if you have any questions on this review lesson on inverse trig, please ask, and I'll see you in the next one. Bye.